Hello everyone, my name is Pegah, and today I will give a presentation for our paper with the title of TextFlow, Screenless Access to Non-Visual Smart Messaging. In general, on-screen keyboards, such as VoiceOver, supports text entry on mobile devices by displaying a visual layout of letters, but they continue to pose significant challenges for people who are blind or visually impaired. In particular, when a blind is on the go and has to keep the cane in one hand. In addition, users have to initiate an open-ended text composition despite sending the same messages frequently. Existing work on mobile texting for BVIs can be divided into three broad categories. The first is the screen-centric technologies such as Braille that requires users to continuously move the finger on the screen to find and select the intended letter. However, this can be problematic when BVIs are walking with a cane. The second method is voice input that allows users to send a text message via voice. But in this case, privacy can easily be broken, especially in public spaces. The last method is a screenless text input such as KeyFlow that uses a wearable device to enable typing using in-air gestures and without the need for a reference screen. However, this method can increase the cognitive load over time and may unnecessarily fatigue the hand muscles. So we ask the following question: can we reimagine entirely non-visual texting in a way that is quiet, proactive, and untethered from a screen? To explore this question, this paper introduces TextFlow, which is a mixed initiative context-aware system that generates short, entirely auditory message options relevant to the user's current context, such as time or location. Users can listen to suggested Aural messages using a finger-worn device in order to send a text message. Now, to demonstrate how the system works, I display an example of TextFlow that shows a person who is blind interacting with the system using tapping gestures in order to send a text message.
Get to a location. Signal my location. Check in location. Shopping. Waiting. Shopping. Check in location. Check in location. Selected. Have you arrived? I'm here. Are you coming? Are you here at Starbucks? Are you here at Starbucks? Selected.
In order to inform the design of TextFlow, we conducted a study with 20 BVIs aimed to elicit the topics of conversation based on their situations. Studies were conducted remotely for a total of 1 hour. Interview questions were focused on places that BVIs typically go and modes of transportation, as well as the situation in which they send a text and the types of text messages they send. After performing thematic analysis from interview responses, we were able to find 6 high-level themes that represent different types of text messages participants send on a regular basis. This includes notifying someone, offering help to others, scheduling or rescheduling plans, coordinating with others, reminding others, and requesting help. Each type of text message corresponds to 3 or more topics, such as arrive late, meeting, and shopping. Overall, 17 specific topics emerged from our study. In addition to topics, we were able to identify specific situations in which some of these topics emerge frequently. As you can see in the figure, these situations include in vehicle, on foot, inside or nearby point of interest such as a restaurant, and frequently visited places such as work. Later, for each topic that is elicited from the study, we generate a list of short text messages. Messages are retrieved and refined from a public benchmark called Weibo that contains more than 4 million short text conversations. Given a reference message sample from the study, we used an AI model called Roberta to retrieve sentences that have entailment and contradiction relationship with respect to the query, and we rank them based on the probability scores. Based on the results of the user study, we develop TextFlow that is composed of three main components. First is the user model that combines user situation with personal related commitments in order to generate a dynamic profile. And the system suggests and ranks topics based on the user model data. Reasoning model provides a set of rules that are learned from the user study, and each rule is associated with one or three topics. When a rule is activated, the system automatically suggests to the user the topics associated to that rule. Finally, a list of topics and messages are fed into the task model for interaction using a finger-worn device that supports 5 tapping gestures. Users can browse and listen to system suggestion to send a text message without relying on a reference screen. More details on each module can be found in the paper. When referring to the user model data, the user situation is represented as the ontology of location, time, and activity. Location is represented as longitude and latitude. Activity is classified into 3 categories of still, on foot, and in vehicle. Personal related commitments is elicited based on the data available in the calendar. We then performed a user study with 10 BVIs who interacted with the TextFlow through a series of 15 tasks. Examples of scenarios and tasks included on my way to meet a friend at a Starbucks at 2 p.m., and the task was letting a friend know I will be late. We then computed the average task success rate, which was 88.6% across all the 3 scenarios. On average, 4 out of 15 tasks had a 100% success rate across all 10 participants. In the remaining 11 tasks, an average of 1.6 participants per task had partial success, and an average of 0.72 failed. We then performed thematic analysis from participants' responses to interview questions. A common theme that emerged was bypassing the phone. Participants mentioned TextFlow enables easy access to important activity of everyday texting. For example, one participant commented, "The system helps you send text messages without using your hands for the phone, and so you could use your cane and fully concentrate on traveling as opposed to texting and traveling at the same time." Another theme that emerged was privacy, efficiency, and accuracy of TextFlow with respect to accessible keyboards and dictations. For example, one participant said, "With dictation, I have to speak. Everybody else can hear what I'm saying. But if I was using this system and I had earphones on, nobody else can hear. So there is privacy, which is a big deal for blind people." To conclude, in this paper, we introduced the notion of TextFlow that enables texting without relying on a reference screen. The system is a mixed initiative that supports entirely auditory accessible interfaces in a screenless mode using a wearable device. The result of our study shows that participants' interaction with the system was successful across all the tasks. Based on the findings from the study, in the future we plan to augment the message samples for each topic, as well as to make system suggestions more personalized. We would like to thank NSF for its financial support in this research, along with the research participants and assistants for their input to this work. Thank you.